In today's lesson, we're going to be talking about function notation. So we have a function here, f. Again, every function, its input is always its domain of f, and its range, its output. The image where that function goes to is always denoted as r subscript f, so it's range of f. So the function notation here, typically have a function, let's say f, and the input is expressed as x, and the output is expressed as y. In this case here, f acting on x equals y. So let's take a look at the applications of function notation with the following examples. So for our first example here, we have a function f at x is equal to 2x squared minus 5. The idea here is the input of the function, whatever goes inside those brackets, that's the input of the function. So a lot of people will view this as, let's say you have f at box is going to be 2 times box squared minus 5. And the idea behind that is whatever goes inside the box is what goes in place of x. So whether that's just a t, then it just becomes 2t squared minus 5. Or if it's a sequence of terms, in this case t minus h, this would be 2, in place of the x, we put a t minus h, quantity squared, minus 5. So the idea here with function notation is, again, that input is a placeholder, right? The placeholder for x. So continuing on with this idea here, you can be asked what's f at y? Well, f at y would be 2y squared minus 5. What is f at t? F at t, as we just discussed, is 2t squared minus 5. And continuing on, what's f at like t plus 2 is going to be everywhere I see an x, I change that to a t plus 2 quantity squared minus 5 is the idea. If someone asks you what is f at a plus b plus c, again, that's going to be 2a plus b plus c quantity squared minus 5. And the idea behind this, again, is that the x value is a placeholder for, in this case, y, t plus 2, or a plus b plus c. Let's take a look at some examples. So for our first example here, we want to evaluate the following function at different values. So in this case here, f at a half. The function a half here, everywhere that you see a t, here, here, and here, you're going to change that to a half, in which case this will be 1/2, 1/2 minus 3, 1/2 plus 4, and that becomes 1/2 over, and what is that, negative 5 over 2, and this becomes here 9 over 2, and we get 1/2 over negative 45 over 4. And whenever you are dividing fraction by fraction, as you guys know, we change that to multiplication, so this becomes 1/2 times 4 over negative 45, and flipping, and this becomes negative 2 over 45. Continuing on here, we look at f at t minus 2, and again, everywhere you see a t, we're going to now change that to a t minus 2. So this becomes t minus 2 over t minus 2 minus 3, t minus 2 plus 4 is t minus 2, t minus 5, t plus 2. And now our simplified expression here is t minus 2 over t minus 5 times t minus 2. Let's take a look at the next example. So now we want to look at f at 0. So everywhere I see a t, I change that to a 0. So it becomes 0 over 0 minus 3 times 0 plus 4. And as we know here, that final answer just becomes 0. And we got f at 1, in which case that's 1 over 1 minus 3 is negative 2. And 1 plus 4 is 5. And this becomes negative 1 over 10. So we have f at 0 is 0, and f at 1 is negative 1 over 10. Let's try another example. So for the following example here, of f at x is the square root of x minus 9 over x plus 11. So in this case here, everywhere I see an x, so everywhere I see an x, I'm now changing that to an x plus h. So this will become the square root of x plus h minus 9 over x plus h plus 11. And continuing on here, this is going to be now, the function is acting, its input is only the 25, it is not the plus 1. This is external. So you're going to be evaluating f at 25 and then taking that output and adding 1. In which case here, this becomes f at 25 is going to be the square root of 25 minus 9 over 25 plus 11 plus 1 is the square root of 16 over 36 plus 1 is going to be the square root. Now when you take the square root here, you can take the square root of the top and square root of the bottom, in which case here this becomes 4 over 6 plus 1, which becomes 10 over 6, and in the lowest terms we get 5 over 3 for this example here. Continuing on here. Now we've just evaluated f at 25. In the previous example, we found that f at 25 was equal to 4 over 6. So this just becomes negative 2 times 4 over 6, in which case you get negative 4 over 3. Continuing on here with the next example, this becomes f at x plus 2 minus 9 over x plus 2 plus 11 minus x minus 9 over x plus 11 is x minus 7 over x plus 13 minus x minus 9 over x plus 11. At this point here, we would just leave this, but again, the idea here is that everywhere you see an x, you change to an x plus 2, minus everywhere you see an x, we just keep it back as an x, our original function here. All right, taking a look at our next example here, we have f at x equals x plus 1 over x minus 2, in which case here, f at a half is going to be 1/2 plus 1 over 1/2 minus 2. And simplifying this here, we're going to get 3/2 over 1/2 minus 4/2 minus 3/2, and you get minus 1 for that question here. And this is f at 0. So everywhere I see an x, I change that to a 0, so it becomes 0 plus 1 over 0 minus 2 is minus 1/2. All right, let's take a look at the next example. For the next example here, we want to find all value or values of x such that the following equation is satisfied. Obviously, we're going to need a definition of what f at x and g at x are, and they do give it to us here. It's f at x is x squared minus 7, and g at x is x. So let's put that in the equation here. We got x squared minus 7 over x is 6. Multiplying across by x, we get x squared minus 7 is 6x, and hopefully this is some simple factoring. Bringing everything to one side here, we see this factors into x minus 7, x plus 1 over 0, and I get two values of x, negative 1 and 7. So when x is negative 1 and 7, we notice here that the ratio of the function f at x and g at x is going to be 6. Let's take a look at another example. In the following example here, we're given two functions. One is 2x minus 3, the other is x squared plus x plus 1. And again, we want to find all values such that now the two functions are equal. So equating these here, we have 2x minus 3 is going to equal x squared plus x plus 1. And again, whenever solving this, you just bring everything to one side, in which case we get x squared minus 2x plus x plus 3 plus 1, and I get 0 is x squared minus x plus 4. And taking a look at this here, again, if you want to see whether you can factor this or not, you can do a quick check using the discriminant. If I go to calculate the discriminant with this quadratic here, we get negative b squared minus 4a, in which case I end up getting that the discriminant is less than 0. So calculating the discriminant here, we get a discriminant less than 0, in which case there are no such values. And again, to remind you here, when your discriminant is less than 0, that means that your following quadratic here has only complex roots. Therefore, there's no real values such that these two graphs intersect. Let's take a quick look at the sketch of both these graphs on the same Cartesian plane. So taking a look at both of these graphs on the same screen here, you'll see here we have our y equals 2x minus 3. And then we also have our y equals x squared plus x plus 1. And you can clearly see here the quadratic function and the linear function do not intersect anywhere here, which is why we had complex roots. All right, that concludes today's lesson on function notation.